today we're going to go over acceleration, which the concept of is review. Okay, we went over what acceleration was in Science 10. Okay? The first formula we go over will also be a review, like in Science 10. What will be new is that we will be looking at about 4 new formulas. Okay, those are on your formula sheet, but I'm going to go over them with you today. Okay, we'll go over sample problems for each of the new formulas. I'll show you all the manipulations of the formulas, okay, so that you can kind of see how they work. Now, the one thing I'm going to caution you about, because I see people do this every year, when I'm showing you the manipulations, okay, I have seen people who just take out their formula sheet, or take out a sheet of paper, and they write down all the manipulations. Okay? And then they're like, sweet, I have them all. Now I just have to look at this sheet. Except that sheet won't be with you on a test or a quiz. And I don't want you to be in a panic because you wrote down the manipulations instead of learning how to manipulate. Okay? So make sure that when I'm manipulating, you're following the steps that I'm doing. Just basic algebra stuff, which I will review today before we start that. Okay? All right, so key points for today. Understand what accelerated motion is. That's review. Okay? Learn the relationship between change in velocity, distance, time, and acceleration. Some of that's review, some of it's new. Okay? And be able to solve accelerated motion problems. You did some of that last year. You're going to do more of it this year. Okay? The reason we have to go over acceleration again, okay, and in more detail, is because it is part of projectile motion, which is the last thing in this unit. And it is huge in Unit 2 when we're talking about forces, because forces cause objects to accelerate. And so we deal with a lot of accelerating objects in Unit 2 as well. So we have to have all of that kind of worked out and be very familiar with what acceleration is, how it works, and the formulas associated with it. Okay, questions there? All right, don't be afraid to ask as we're going along, guys. Okay, anytime the velocity of an object is changing, the object is accelerating. Okay? In physics, we do not use the term decelerate. Okay? And acceleration is any change in velocity, positive or negative. Okay? Any change is an acceleration. Acceleration can be negative, okay? Which would mean it's either slowing down in a positive direction or speeding up in a negative direction. Okay? Or both, depending on the motion. Right? But that's what we have to look at there. Okay? All right, now average or uniform is probably a better word to use here rather than average. Okay, we'll say uniform acceleration is best illustrated by a plane that's taking off. Okay, a plane that's taking off is a good example of uniform acceleration, way better than a car accelerating away from a light. Okay, why is a car accelerating away from a light not a good example of uniform acceleration? Maybe I should have started with, what does uniform mean? Okay, uniform means it's constant. So if I was looking at a graph of uniform acceleration, it would look like that. Okay, the velocity would change by the same amount every second. Okay, so why is a plane a good example of that and a car not?
Because for cars, stopping to start it has to use energy, and that usage of energy probably isn't as equal as the building of momentum that plane does.
You're on the right track. You're right, it's not as equal. Okay, that's what we're going for here. What does a car have that a plane doesn't? Okay, well, you're right, a plane doesn't have a pedal, it's got a bar, right? The throttle bar.
Plane has to go up, but a car goes on a relatively flat plane, I'm assuming.
You're absolutely right, I should have clarified. I meant just when the plane's on the runway.
Oh.
I should have clarified, you're absolutely right. Okay, so the plane's just on the runway, just before takeoff. Okay, why is that more uniform than if I put a car on the runway beside it and had the car try to keep up and do the same thing? You have to change these in a car. Sometimes it's done for you. Gears. Transition. Okay? Your car has a transmission and it has gears, and it's constantly changing those gears to provide you with the ability to go faster. Okay? Because first gear, okay, this might be a little alien to you guys. How many of you have actually driven a manual transmission vehicle? Wow, that's like the highest number in a long time. Okay? They're going the way of the dodo. Most people don't even know how to use them. third pedal. I actually watched a person get into a car once and I'm like, is that the front brakes and the back brakes? I'm like, oh my God, get out. You can't drive this car. Okay. But yeah, so if you've ever driven a manual, gears lean a little bit more than if you've only ever driven an automatic. Okay, but first gear will only get you going so fast. But first gear also provides you with the greatest rate of acceleration. It is the most kind of powerful gear. Okay, it has the lowest kind of ratio on it, so it can pull hardest. Okay, but it can only pull you to a certain speed before your engine is revved out. Okay, then it switches to another gear that is a different ratio. Okay, now your engine can rev to its maximum, but you can go faster. Okay, it doesn't accelerate as fast, but it can get you to a higher velocity. Okay, and so on and so on. Okay, if you've ever driven a stick and you've tried to pass somebody on the highway, you don't just push the pedal down while you're in 5th or 6th. Okay, you'll die because you get no acceleration out of those gears. If you drive an automatic, you just push the pedal down, and what does the car do? Yeah, it shifts down 2, 3, depending on how many gears your transmission has, 4, okay, gears down. If you have that new 10-speed transmission that they're putting in some of these vehicles, okay, it'll shift like 4 gears down in order to give you enough acceleration or power to make that pass safely. Okay, if you were in a manual transmission vehicle and you left it in the highest gear and just pushed the pedal down, you wouldn't have any acceleration to get around. Okay, so a car doesn't have a graph that looks like this when it's accelerating. It has a graph that looks like this. Okay, that's not uniform. Right? As it changes gears, its ability to accelerate or change its velocity decreases. Its ability to reach a higher velocity gets better, but its ability to change its velocity decreases because there's less and less kind of power available. Okay? All right, so this is uniform acceleration and would be governed by y equals mx plus b. Okay, so pretty much all the accelerations we deal with are going to be uniform accelerations. We're basically never going to deal with this situation unless it's kind of a one-off. Okay. All right, now it is from this formula that we get this formula, okay, which you learned last year in Science 10. Acceleration is the rate of change of velocity, the change in velocity over time. Okay. Now, that means that on this graph, if I've got meters per second and seconds here, that what part of this line will be the acceleration? Y, m, x, or b? M. Okay? Remember, acceleration is the change in velocity. Velocity is on the y-axis here, right? Okay? Over time. X is time. So if I manipulate this for m, okay, there's VF, there's VI, over x, x is t, okay? That's where that formula comes from, okay? It's finding the slope of the line or the rate of change of velocity for this graph, because that's what acceleration is. It's how many meters per second your velocity changes by every second. Okay? Everybody all right with that idea? Okay, what are the units for acceleration? Meters per second squared. Okay, now that doesn't mean that they are squared, it simply means this. If I divide meters per second, okay, by seconds, okay, what happens when we try and divide fractions? What are we supposed to do? Right, multiply by the reciprocal. Okay, so basically we take this. Okay, we've got 1 over seconds. Meters times 1 is meters. Seconds times seconds is seconds squared. Okay, really what we're saying is it's meters per second. Okay, that's acceleration. Meters per second, but we abbreviate it meters per second squared. Okay, they're mathematically the same thing. All right, so that comes from this formula here, because I'd be dividing meters per second, which is my change in velocity, by time in seconds. So meters per second divided by seconds. Meters per second per second. Okay. Everybody all right with that idea? Okay, that's Science 10 review. We did that in Science 10. We learned velocity versus time graphs, slopes of acceleration. Here's this formula. Okay. All right, so if we're looking at this example here, so I've got this plane starts from rest. Is that an important term? Yes. Okay? If something starts from rest, its initial velocity, or VI, is 0. If it comes to rest, which one is 0? VF. Okay? Rest always means it stopped. Okay? But you have to read the question carefully, see whether it starts from rest or comes to rest. Okay? Because it makes a difference. All right, so this one starts from rest at time 0. The plane accelerates down the runway, and 29 seconds later is traveling at 72.2 meters per second, where the plus sign indicates to the right. Okay? Determine the average acceleration of the plane. All right, so this question gave me VI, it gave me time, and it gave me VF. And it wants me to find acceleration. Okay, do I have a formula that will do that? Okay, one I learned last year in Science 10. Acceleration equals VF minus VI over T. Okay, here's why writing down your givens is so important. It wasn't obvious in Science 10 why it was so important to write down your givens. But you've got, when we're done today, 5 different acceleration formulas. Writing down your givens will help you determine which one of them you need to use in the question, because it'll be, match it up with what you have and what's in the formula. Okay, for this one here, I have these 3 things and I'm looking for this, and they're all in this formula together. Right, so I don't have to manipulate, I'm just going to plug in my numbers. So 72.2 minus 0 divided by 29 seconds. All right, so this thing is accelerating at 2.5 meters per second squared. So after 1 second, how fast will it be going? 2.5 meters per second. How fast after 2 seconds? 5 meters per second, and so on and so on. Okay, that's how its velocity is going to increase. Okay, every second it's going to be going 2.5 meters per second faster than it was the second before. Okay. All right, everybody okay with how we did that? All right, do I have the right number of significant digits? Okay, how many significant digits does this have? 3. How many does this have? 2. How many does this have? None. Can't measure 0. That kills people. Okay, I don't know why, but people, they look at, if I write 0 as one of the things in a question, they assume that it has one significant figure. 0 is infinitely accurate because I can't measure it. Okay, so if something ends up, one of your givens is 0, it does not affect your significant figures. Okay, you can't measure what you don't have. Okay, only measured values contribute. This is my lowest number of significant digits, so my answer has 2. Okay. All right, any questions on how that formula worked? Okay. So that's the math we just did there, but obviously far neater than how I drew it. Okay. All right, here are your other 4 formulas. Okay, I'm going to go back and show you the manipulation of the first one here in a second, but these are your other 4. You don't need to write them down because they're on your formula sheet. Okay, and I think I'm just going to break down and photocopy you a formula sheet because I'm just tired of you having to look on your phone for it. Okay, I'll sanitize my hands before I hand them out. All right. So we'll be looking at how all of these work, okay, and kind of where we get them from. Okay, these 2 here actually have to do with calculating the area under the line on your velocity versus time graph. I'll show you how those were arrived at. Okay, this one not really so much to do with graphing. There's a little bit there, but okay, this one's very useful for projectile motion problems. Okay, and then we have this last one. Okay, where D equals VF plus VI over 2. When you add 2 things together and divide by 2, what are you calculating? Any 2 things and divide by 2. Average. Yeah. This actually calculates average velocity and multiplies by time. Okay? So this formula is really just this. which is fine as long as the acceleration is uniform, like it's one section of a graph. If it's over a whole graph, it's not as good, okay? Because the acceleration may not be uniform over the whole graph. So it's probably the least useful of all of the formulas, and you can only use it if the question specifically states the acceleration is uniform, okay? All right, let's go back and look at manipulation of this formula here. Okay, 3 rules of algebra. What are they? If I want to move something, okay, that's rule number 2. What I do to one side, I do to the other. If I want to move something, I do the opposite. That's rule number 1. It doesn't really matter what order, but okay, they're both rules. Okay, the 3rd rule, move what's not attached to what I'm looking for first. Okay, those are my 3 rules of algebra. So if I'm looking at this formula here and I want to solve for VF, what do I move first? T. T is not attached to VF. VI is. Okay, so I'm going to multiply both sides by t because to move something I want to do the opposite. Right now I'm dividing by t. So I multiply both sides by t. T cancels. T comes over here. All right. Now I want VF by itself. How do I move VI? I add it. Yeah, because I'm subtracting it on this side. So I would add VI to both sides. So VI plus t times a equals VF. Now I just want to back up one step. T times a equals VF minus VI. Okay, so t times a gives me my change in velocity. Everybody all right with that idea? Okay, so when I'm looking for VF, does it make sense that I would add my initial velocity to the change in velocity? Right? You think about it. If you go to work, and at the start of the workday you have $5, okay? Over the course of the workday you make another 50. How much do you have at the end of the day? 55 bucks. That's what you just did there, okay? You took what you started the day with and you added how much you made during the day, and now you got your final total, okay? That's what you're doing here. This is the initial velocity, how fast I was going. Here's how much I changed my velocity. That gives me my final velocity. Okay? Now, with that logic, whoops, too many things up here. I want to solve for VI now. What do I move first? T. Okay, multiply both sides by t. Okay, now what? Okay, I can subtract VF, but if I do that, what is going to be problematic? What about VI? VI will be negative. If you're okay with that, you can manipulate the formula that way. I always forget that when I do that, VI is negative. I forget at the end of the question I have to switch the sign over. Okay, I always forget that. So what I do is I actually add VI over here, and then I subtract t times a over here. Okay, is it okay for me to do that? Yeah, because before I added these two things together, would I have multiplied these? So it's okay for me to move that all as one chunk then, right? Okay, so just a minute ago, well actually right now, we said that VI plus the change in velocity equals VF. So does it make sense then that VI should equal VF minus the change? Right? To find VF, I took the change and I added it to VI. To find VI, I take my final and I subtract the change. Back to our money example, I end the day with $55, okay? At the beginning of the day, I had 5, the change was 50, right? If I take 55 minus 50, I calculate how much I had at the beginning of the day. That's what we're doing here, okay? All right, either way is fine. Whichever way makes most sense to you, I'm okay with. I just know that for me, I always forget to switch the sign after. Okay, when I do it. All right, and then obviously to calculate time, that's the one we didn't look at. Probably the easiest. Okay, if I want to get time by itself, what do I do? Yep, first I have to multiply both sides by t. Okay, reason for that, I cannot solve for something if it is on the bottom of an equation, because I'll be solving for 1 over it. Now that's what I'm looking for. Right, so now what do I do with a? Divide it over now. And so basically you're just like cross multiplying to get t. Everybody okay with those manipulations? Hopefully that seems familiar, because you would have had to do those same manipulations last year. Okay, I want you guys to try that one. That uses the formula we just went over. So we have a hybrid car with an initial velocity of 10 meters per second east, accelerates at 3.0 meters per second squared east. How long will it take the car to acquire a final velocity of 25 meters per second east? So first step, write down our givens. So we have an initial velocity of 10 meters per second east. So that's VI. 10 meters per second east. Okay? And it accelerates at 3.0 meters per second squared east. So they just gave me A. And I can tell that from the units. And the question said it was accelerating at that rate. So meters per second squared east. Okay? So far everything mathematically is positive. Right? I don't have anything that's backtracking. Right? And then it says, how long will it take, which means I'm looking for time, to reach a final velocity of 25 meters per second east. All right, everything's east, so I don't have to worry about anything being negative. Right? I just have to pick a formula. Well, this formula has everything in it that I was given, so it's my best choice. I need to manipulate it for time. Okay, so if this was a question on, let's say, a test or a quiz, you get 1 mark for your givens. You get 1 mark for picking the correct formula. Then I'd have to manipulate, so multiply both sides by t, divide both sides by a. Okay, so you'd get another mark there for manipulation. Okay, manipulating correctly. Sometimes I give another mark for plugging in the numbers, but not always. So in this case, we're looking at 25 minus 10 over 3. Okay, so 25 minus 10 is 15, divided by 3 is 5 seconds. Okay, do I need a vector on that? No, time is scalar. Okay, even though we talk like it isn't. Oh, it's just an hour east of here. We say that all the time. Dumb. That's one of those weird things that we do that's wrong. Okay? All right. No questions there? Everyone's okay with that one? All right. These two problems both involve using that formula. But there's one trick here in number 2 that we need to talk about. And that is that they give the velocity in kilometers per hour. Okay? Then they give the acceleration in meters per second squared. Can I use those two things together? Okay, I have to convert my velocity from kilometers per hour to meters per second. Okay, so we need to look at how do we do that. Okay, well, we have to do what's called a compound conversion. So I have kilometers per hour, and I'm trying to go to meters per second. So I need to convert both the kilometers and the hours. Okay, how many kilometers, or how many meters, sorry, in a kilometer? 1,000. All right, so whatever I have here in kilometers, okay, to get it into meters, I'm going to multiply by 1,000, because there's 1,000 meters in a kilometer. Okay, so basically I'm just making a conversion factor here. 1,000 meters is 1 kilometer. Okay, and how many seconds in an hour? Everybody wants to say 60. It's this knee-jerk reflex, but it's not. There's 60 seconds in a minute, 60 minutes in an hour, 60 times 60, 3,600. Okay, so in 1 hour, there are 3,600 seconds. Okay, so I have to take what I have in kilometers per hour, multiply by 1,000, and then divide by 3,600. Is there a shortcut for that? Okay? Okay, can I reduce that? 1,000 over 3,600? I'm pretty sure I can do this. Kilometers per hour times 1 over 3.6. Same thing. Okay, what's kilometers per hour times 1? What's anything times 1? Itself. So, here's the shortcut. Take what you have in kilometers per hour divided by 3.6. You'll have meters per second. Want to go from meters per second to kilometers per hour? Do the opposite. Multiply. Okay? That's what we call a compound conversion. Okay. It probably wouldn't hurt to just remember that when it comes up often enough. Okay? Kilometers per hour to meters per second divided by 3.6. Meters per second, kilometers per hour, multiply by 3.6. Okay? 3.6 is the magic. Okay, so keep that in mind for number 2. You're going to want to convert your kilometers per hour here to meters per second, and then you're going to have to convert it back to kilometers per hour for your answer. Okay, so the answers are right here. You can check them as you go. I'll give you a few minutes to try those 2, and then we'll walk through them together. Okay, so for number 1, we got this motorcycle has an initial velocity, so they give us VI, okay, of 6 meters per second east. Okay, accelerates at 4 meters per second squared east, so they gave me the acceleration. Okay, how long will it take to reach 36 meters per second east? So exactly like the example we did just a second ago. Okay, we're just solving for t, so I'm going to use a equals vf minus vi over t. I'm going to manipulate for t by multiplying both sides by t, dividing by a. Okay, so that'll be vf minus vi over a. 36 minus 6, okay, divided by 4. Okay, so we got 30 over 4, which should give us 7.5 seconds. Are you all right with that one? Okay. Are you ready to go over number 2? Okay, so for number 2, we have an elk moving at 20 kilometers per hour north. So that's my VI, at least it sounds like it. Okay, but the first thing I need to do is convert that to meters per second. So 20 divided by 3.6, okay, it's giving me 5.5 repeating. I need to keep all those decimals when I do this. Meters per second north. Okay, and it accelerates at 1.5 meters per second squared north. Okay, for 9.3 seconds until it reaches its maximum velocity, which is what I'm trying to find. Okay, so find that in kilometers per hour. So I'm going to find it in meters per second, and then I'm going to convert it back. Okay, so I'm going to take A equals VF minus VI over T, because it's the formula I can use with the information I'm given, and solve for VF. So multiply both sides by T, okay, add VI to both sides, and I'm solving for VF. All right, so that'll be my 5.5, repeating, plus 9.3 times 1.5. That will give me VF. Okay, so now in my calculator, I'm going to take that number, okay, as it stands, so just put in the answer, okay, plus 9.3 times 1.5. All right, so that gives me 19.505, okay, meters per second. They want that in kilometers per hour, so I multiply that by 3.6, 70.22. I only have 2 significant figures, so it's 70 kilometers per hour. North. Okay, is acceleration a vector quantity? Absolutely it is. Okay, because you can be speeding up, you can be slowing down, accelerating negatively, accelerating positively. Acceleration is a vector quantity. That's going to come into play as we get into some other questions. Okay, so you're going to need to make sure that you're reading the question carefully so you know whether VI is negative or positive and so on. Okay, so it's going to become important as we go along. Okay, so here's our next one. Question.
If it's a vector quantity, why doesn't it have a little symbol?
It actually does. I just keep forgetting to draw it on. You give me that look like I've done something really bad. Okay. Okay. So a cattle train is traveling west at 16 meters per second and is brought to rest. Okay. So VI is 16 meters per second. What's VF? 0. Okay, in 8 seconds. Okay, find the displacement of the cattle train while it is coming to a stop. Assume uniform acceleration. Now, did I mention that one of those formulas would only work if the question specifically stated the acceleration was uniform? I did. Okay, there's also only one of the formulas about accelerated motion that doesn't have acceleration in it. And I have to use that one because obviously I'm not given acceleration. The object is clearly accelerating, but I don't have the acceleration. I'm asked to find distance. So I will be using this formula. D equals VF plus VI over 2 times T. Okay. All right. In this case, do I need to manipulate that formula at all? No, I already have all the numbers. It's already set up to solve for D, which is what the question asked for. So for me, this is simply a matter of plugging numbers into the formula. So that'll be 0 plus 16 over 2 times 8. Well, 16 over 2 is 8. Times 8 is 64. Okay. Yeah, I'm doing better now. I remember to put the arrows over the top. Okay. Of all of them. Okay, so 64 meters west would be my total displacement. Everybody all right with that? Okay. If I need to manipulate this formula, so D equals VF plus VI over 2 times T. If I want to solve for T, what do I do? Well, but if I divide T over, it'll be on the bottom, right? And I can't solve for it on the bottom. Think order of operations, guys. Before I do anything, I'm going to do what's in the brackets here, right? So is what's in the brackets here really just one number? Yes. Can I divide it over to the other side to get T by itself? Okay. If it's all in brackets, I can take it all together. Okay, that's one of those weird things about algebra, is since this is going to be the first step I would do, parentheses of the first thing, I can just take it all together over to this side. Okay, it's really just like saying D equals, because we said this is how you calculate average velocity. I'm really just taking average velocity and bringing it over to the other side. Okay, so I can divide the whole bracket over. Now I'm solving for T. Okay. Still have to do what's in the brackets first, but I can move it all together. All right. What if I want to solve for VF? What should I move now? What's not attached to VF? T. Yeah, I should move T first, especially since by dividing both sides by T, I eliminate the need for the brackets, right? I can't erase the other ones. Look at the big setting. No. Okay. Now the brackets are gone. Is it easy for me to get at VF now? What should I move? The 2. Yep. Okay. Multiply both sides by 2. 2D over T. Okay. What do I do with VI? If I want to move something, I do the opposite. So I'm adding VI, so I subtract VI. So I'd have 2D over T minus VI equals VF. Okay, and it'd be the same if I was solving for VI. It'd be 2D minus VF equals VI. Okay. All right. Questions on how that one works? You're not going to use that one very often. Okay? Only comes up very, very rarely. Like in those two questions. Okay? Give those a try. See how you do with that one. So for number 1, we have a hound running at a velocity of 16 meters per second south. Okay, it slows down uniformly to a velocity of 4 meters per second south in 4 seconds. Okay, what's the displacement of the hound during this time? So once again, I don't need to do any manipulation. Okay, I'm going to be using this formula because I wasn't given the acceleration. Okay, and I don't need to manipulate because it's already set up for D. All I have to do is plug in my numbers. So that'll be 16 plus 4, okay, over 4 times, sorry, over 2 times 4. Okay, so 16 times 4 is 48 divided by, no, it's not 48, 50, 52. No, you know what? I'm not going to do that in my head because that's just embarrassing. Okay, 16 plus 4, not times 4. That's what happens when you get old. Best advice I can give you, don't get old. It sucks. Okay, so we got 16 plus 4. Okay, so we got 20 over 2 is 10. Okay, times 4 is 40. Okay, so we got 40 meters south being the total displacement of the hound. Everybody okay with that one? Okay, how many people have done number 2? Okay. Well, number 2, this is where direction now matters. Okay, if we don't make things, if we don't recognize up the hill and down the hill are different, okay, we can have a problem. Ball moves up a hill with an initial velocity of 3 meters per second. So VI is 3.0 meters per second uphill. Okay, 4 seconds later, oh, here's a good significant digit thing for you. How many significant digits does FOUR have? Hell if I know. That you never write a number that's a measured value as a word. Okay? Because now we don't know how you measured it. You wrote it as 4. Okay, not the number 4, but the word 4. Okay? That does not help me with my significant digits. So I have to assume it's infinitely accurate. So basically that number will not affect my significant figures because I have no idea how it was measured. Okay? I'm just going to say it's 4 seconds. Okay, it is moving down the hill at 9 meters per second. Oh, downhill. Okay, find the displacement of the ball from its initial point of release. So once again, we don't have to manipulate. We have everything and the formula is already set up for what we're looking for. But we have to keep in mind that VF and VI are in opposite directions. VF is -9 because it's down the hill, okay, plus 3, okay, divided by 2, right, is going to, and then multiply by 4 seconds. All right, so -9 plus 3 is -6. Okay, -6 divided by 2 is -3. Okay, -3 times 4. Okay, this thing is going to travel -12 meters, or it should actually be written. Should it be left as -12 meters, or should I write it differently? Yeah, downhill, actually. I need to be specific. Okay, the question said up the hill and down the hill. I can't leave my answer as negative. The question said uphill and downhill. My answer needs to say uphill or downhill. In this case, it's downhill. Are down and downhill the same thing? No. Down is straight down. Downhill is some angle other than 90. Because if you're 90 degrees down, that's straight down. That's not a hill, you're falling. Okay? 89 degrees, it's a hill, steep. Okay? It's not falling. All right. Everybody okay with that? Making sense there? So that's just illustrating the importance of the vectors, okay, in that. All right. Okay. So in this one, I have a golf ball that is initially traveling at 25 meters per second. It hits a sand trap and slows down with an acceleration of negative 20 meters per second squared. So this question gives me VI, 25 meters per second. Okay, and they didn't give me a direction on that, but I'm going to assume that it's positive because they tell me the acceleration is negative and that it's slowing down. Okay, if I'm slowing down, I'm actually accelerating backwards. Okay. Okay. Find its displacement, so I'm looking for D, after 2 seconds. All right, so in this one I have VI, I have A, I have T, and I'm looking for D. Right, so I need a formula that has all of those things in it. Which one is it?
VIT plus half of AT squared.
Exactly. D equals VI times T plus 1/2 AT squared. Okay. Now, 1/2 AT squared does find displacement because taking half the acceleration and multiplying by T squared is essentially taking average velocity and multiplying by time. Okay? Here's where this formula comes from. I have a velocity versus time graph that is a diagonal line. Okay? If I want to find the displacement, we said we would do a calculation that looks something like this. We would find the area under the line. Here, it would be average velocity times time. Or actually, it would be initial velocity times time, because that's what this is, right? This is my VI. Everyone okay with that idea? And I'm multiplying it by the length of time. That's that area of that rectangle. Everybody okay with that? Right? And then up in here, I was going to have base times height over 2, okay? Which is taking average velocity and multiplying by time, okay? That's what this calculation does. So this part of the equation calculates this, and this part of the equation calculates that. Okay? That's where that calculation comes from. It's taken from your velocity versus time graphs. Okay, so for this one, I'm solving for D, which means I don't need to manipulate the equation. So I have VI times T plus 1/2 AT squared. Right, so VI was 25 times, sorry, these are all vector quantities. Okay, 25 times 2, that's my time, plus 1/2 times negative 20. It's crucial that I remember to put the negative in there. Okay, times 2 squared. T squared. All right, so when I do that, okay, so I'm going to have 50 plus 0.5 times negative 20 times 4 is 2 squared. Okay, so the overall displacement of the golf ball, I think it was a golf ball, right? Okay, slowing down, okay, is 10 meters, positive 10 meters or 10 meters forwards. Okay, in this case. Everybody all right with that? Okay, let's look at manipulations of this formula. All right, let's say I wanted to solve for VI. That's probably the easiest. Okay. Yes. Okay, I want to solve for VI. What should I move first? What's not attached to VI? Yeah, this whole thing is not attached to VI. And since it's an addition-subtraction operation, okay, it's saying add these numbers that you're going to multiply anyway. I know what this number was. I can just subtract it over. So I'm going to have D minus 1/2 AT squared equals VI times T. Right, and now I'm going to divide by T. That'll leave me with VI. Does that make this T and this T cancel each other? you have an addition subtraction operation on the top. If this was all being multiplied, then you could cancel the t's. But because there's a subtraction operation here, you cannot cancel those t's. Okay. All right, so that'll calculate VI for me. Everybody okay with that one? Okay. What if I want to solve for acceleration?
The VI times t is separate from the other part, so we just subtract.
Exactly. I'm going to subtract VI times t over first. That'll equal 1/2 AT squared. I want A by itself. What do we do with the half and the t squared? Divide them. Yeah, they're all being multiplied, right? It's 1/2 times A times t squared. If I want to move them, I do the opposite. So I divide both sides by half of t squared. Comes over here. Okay, and I'm solving for A. We just got to follow our rules of algebra. It does get a little bit tricky, okay? But you guys can handle it. Now, speaking of tricky, what happens if I want to solve for t? T's in two places, isn't it? This equation looks kind of quadratic, sort of. It's got t and t squared in it, right? In order to do this, you have to do the f word, factor. Right? Well, since we can't guarantee that you've taken this in Math 20 yet, you won't have to solve for t unless VI is 0. Why will you be able to solve for t without factoring if VI is 0?
Because 0 times t is 0.
Right, because if VI is 0, VI times t is also 0. Okay, so it won't make any difference. If VI is 0 and you need to solve for t, okay, then you're just going, you've just got d equals 1/2 AT squared. Okay, and all you have to do is divide the half and the a over. Okay, so those are gone, and then what? Yeah, square root. Right? So you're not looking for t squared, you're looking for t. Okay? So the good news is you won't have to solve for t if VI is not 0. You will have to solve for t several times when VI is 0. All right. Let's have you guys try those two. Okay, so the first one, you got skier moving down a uniform slope, okay, and you're looking for the displacement. And the second one, you've got this kilometers per hour thing again, okay, so watch out for that. Okay. And you've also got minutes, right? So you got to convert your kilometers per hour and your minutes. Okay, let's have a look at the first one here. So we've got a skier moving down a uniform slope at 3 meters per second. So they've given us VI, 3.0 meters per second. The acceleration down the hill, okay, is 4 meters per second. Okay, so these are all downhill so far. 4. Okay, find the skier's displacement after 5 seconds. All right, so again, I don't need to manipulate here. I just need to plug in numbers because the formula is already set up to calculate d. Okay, so we'll have 3 times 5, so VI times t, plus 1/2 times 4 times 5 squared. Okay, and so when we do that, we should get 65 meters downhill. Everybody all right with that one? Okay, questions on the first one? And we play on the second one. Okay, I'll give you 2 more minutes and then I'm going to go through the second one and then I got a couple of acceleration videos to show you. First thing we have to do is do our 2 unit conversions. Okay, we got to convert 100 kilometers per hour into meters per second. Okay, so VI is going to be, it's 27.7 or 26.7? 0.7, okay, meters per second. I'll actually do that calculation on my calculator so I have the full number here, okay. On a flat road, okay, and it applies the brakes, so our acceleration is negative 0.8 meters per second squared, okay, and it does that for 1 minute, which is 60 seconds, okay. We're looking for D, okay, so we'll have D equals VI times T plus 1/2 AT squared, right? So that'll be our 27.7, okay, times 60 plus 1/2 times negative 0.8, and it's crucial to have the negative there, times 60 squared. Whoops. 100 divided by 3.6. Okay, so now that I've got all the decimals, that's important to have, okay, times 60. All right, so there's the first part of my question, plus 0.5 times negative 0.8 times 60 squared. Okay, give me my 2.3 times 10 to the 2 meters. Okay, I have no vector on this, and that's okay. They never asked for it, okay? It says, how far did the motorcycle travel? That's distance, not displacement, so it's okay to not have a vector on that. Okay, questions on any of those?